Let us continue with the program. It is my pleasure to introduce Stanislaw Janeczko, our first speaker in this afternoon. And he's going to talk on geometric and algebraic restrictions of differential forms. Thank you.
I'm very happy to be here. Thank you for organizers for inviting me here. I'm also grateful for Sidinia, who always inspires me a lot. So this is my pleasure to be here in her presence. Well, I would like to say something elementary, in fact, but some results will be not so elementary. But everything what I want to say is corresponding to invariance of some symplectic structure, so symplectic invariance, but of course it will be hidden in some way. So, you know, in algebraic geometry we represent the sets of varieties by ideals, by algebraic objects, and like ideas of functions and so on. How it is in, if we consider differential forms. Differential forms is a bit different, but of course ideologically the same, but technically a bit different. So if you have a form, omega, so then you have, say, some submanifold, which is on the manifold on which this form is defined. Then of course you might define something what is called like, and that is well defined because at each point of L we have a tangent plane and so on. Everything is well defined, the kind of pullback of the form. If you have, say, form which is so then this is, as I thought, very well defined. These elements, these differentials, are kind of linear objects, say local linear objects, infinitesimal. But that one is a function. There are functions and non-linear. But that's, then, of course, there is another situation, completely another situation if L is singular. If this is a variety with singularities, then you are not able to say what is this for the singularity. So then is good to define, say, restriction, in some way restriction to V, which is singular, in a bit different way. But at first, what kind of forms how they vanish on that? So they vanish, so we say this is 0 if Ik belongs to the ideal of V. Then, of course, all forms on a variety are modulo of that. So it's easy to see also that in those vanishing forms in here, all of that are included. No, that's okay. This is a kind of simple explanation what I want to say, because this is for singular variety V. That element we have to, in some sense, define in different way. Of course, we can consider the tangent, Zariski cone and so on, but that's a different story. But it's not here. Then, so let's start with very elementary definitions, because the aim is symplectic invariance. So let's start from, you will a bit know about symplectic structure. Maybe he's not often here in this workshop, but so symplectic manifold is a pair of manifold which is even dimensional, and symplectic form, or two form which is non-degenerated, close to form, as you see there. And then there are coordinates, at least locally, in which this form has such a nice local form. And then, of course, as for each structure, the structure group is a group of isomorphisms. I mean, those automorphisms which are diffeomorphisms which preserve the structure. So here, these are we call them symplectomorphisms. So symplectomorphisms are such transformations which preserve that structure. And then symplectic geometry is very important also for physics, but because this is a very naturally defined energy. Energy is very important in our life, not only distance, which we have to go from Europe to Rio with some problems because of virus. So symplectic invariance is, but it's a different metric and with viruses. Symplectic invariance is something like that. If you have, say, two germs of subsets, so we call them symplectomorphic if one is transformed into another one, and so on. Geometric restriction, which I try to define here, is something like that. You know, you take the symplectic form and the smooth submanifold, that's no problem, and you restrict it to tangent bundle. I mean, you know what's this is possible to know how to act. And then geometric restriction is a complete symplectic invariant. If you have this guy, then it's not changing if you change by symplectomorphism. It's always the same form, whatever you do. Well, that's to some extent obvious. Then there is a natural theorem of Darboux-Giventhal which says that if we have germs of two submanifolds of symplectic manifold, then they are symplectomorphic, if and only if the germs of geometric restrictions are diffeomorphic. So geometric restrictions are fundamental. And then the natural corollary is all non-singular hypersurface germs in symplectic manifold are symplectomorphic. So if you have a hypersurface, then all hypersurfaces are isomorphic, I mean symplectomorphic. So that's very convenient to some calculations. Then geometric restriction in the linear case is very special case, and we considered it with Zbyszek Jelonek some time ago. This seems trivial, but not very trivial and not finished yet. I mean, do you see this is, if you have symplectomorphism, which is like that, that means that you take two vectors and you plug them changed by this automorphism. Whatever. It's a symplectomorphism if it preserves like that. But, of course, it might be like that on some subsurface, linear, of something like that. And then what is this? This is some restricted property of invariance or something like that. So if you have linear subspace of M, then such objects, already I told, are symplectic invariants. And now if we forget that F has to be symplectomorphism, but any automorphism of a space with symplectic form, then F, say, let's only assume that F preserves symplectic data on some linear space. Symplectic only on L. What does it mean? That's the same formula, but restricted to L. The vectors are from L. So then there are questions, you know. Assume the linear symplectic data are preserved. Does it determine interesting transformations of symplectic space? What does it mean for this automorphism? Is this symplectomorphism or something different? Is this so strong condition that it already pressed for this automorphism to be symplectomorphism, or maybe not? And also, is this possible? Because there's always in physics also, it's possible to collect some information on some subspaces, say, to find energy here, and then tell about energy in general. Well, this is also a question here. Yeah, if it is possible to collect information from a finite family of subspaces and construct a complex system of invariants for the symplectic group? And then we answered these questions with Zbyszek some time ago, and then for that, very quickly I tell, this is, we constructed, to say, coplanar systems, which are just proper to collect this information. Well, this is something what is obvious in this group. So So we have this the linear subspaces belonging to Grassmannian are coplanar if the X is a hyperplane containing all these points. If does not exist, then they are not coplanar. And then the result was that linear automorphism, you have linear automorphism, and then this Lagrangian linear subspaces are not coplanar. F preserves symplectic form to some power on these linear subspaces. Then F is an epsilon k symplectomorphism. So say it's not exactly symplectomorphism, but very close to symplectomorphism. Say this is a root of unity, this epsilon k. So then that's also we are very surprised that this is so, but it's so. So you see that's very strong. It's not necessary to have automorphism checked in each point. It's enough to check in some set of points only, but relatively well situated. Well, then some natural corollaries. And now let's pass to the nonlinear case and the problem which I want to say really today. So let's consider, as in our singularity theories, multi-germs of mappings to the symplectic space. So we have this symplectic space here, and we have mapping. In the image is a symplectic structure. So they are symplectically equivalent if the following diagram commutes. So that's obvious, you know, this is F and G, and psi, this one in the image, has to preserve symplectic form. So then this is a question which was considered by some groups of people, Wojtek and others. Yeah. And then let's restrict ourselves to curves. The curves in symplectic space. The curves in symplectic space are quite important because it seems that symplectic form is defined in somewhere in singularities of this curve some rest of important energy, something what is impossible to change. So this is for curves, it's the same. And then what's a natural standard definitions? You remember a codimension, yeah, codimension of F, as usual. As usual was, you remember, that was a deformations. Here were all vector fields along F, because they are all deformations. You see this is defined here. Is a vector field along F. And then here, as a mother notation, there are tangents. This is the image. Yeah. So there are vector fields working on, you know, germs of vector fields over respectively on C to N. This one, which is here. So then this is codimension of F, usual codimension, if the group of equivalence is differential group. And then symplectic codimension, what's the difference? The difference seems not huge, but it's important and difficult to work with, in fact. The difference is only here, that the vector fields which are here are Hamiltonian vector fields. And Hamiltonian vector fields are not so easy because the Malgrange-Mother preparation theorem is not working anymore. So it's impossible to use these techniques. So each technique should be kind of from the case to the case. The Hamiltonian vector. And then there's the difference, you know, symplectic codimension. And then, as obviously, this is bigger or equal from the codimension, usual codimension. Bigger because this is the kind of subspace. No, that if this is subspace, then this is of course bigger. So then symplectic defect is a very nice invariant which we studied. This is this investigations are done with Go Ishikawa here. And then let's say strict to plane branches, which was a problem also worked which has been by Zariski. So we calculate this symplectic codimension, and it appears that symplectic codimension is a delta invariant. Delta invariant is here the formula for delta invariant. So we search for local algebra, which is local symplectic algebra for the singularity. And a few algebras which are here similar to be considered as a main local algebra, which we know from ordinary singularity theory. So delta invariant is it appears that it's a symplectic invariant. So then proof of that is, well, if you go through some calculations in Zariski papers on that, so you don't find only the symplectic structure, but you find a prenormal form, which is just symplectic form. So this, you see, we construct the vector fields, and yeah, and then we have this exact sequence, which is helping us to prove that this equality is defining, is proving that fact. So there are some algebras here, differential algebras, which are defined, which are also very nice to represent, say, symplectic defect. You see, this is the dimension of such algebra. So then, and also, symplectic defect is also A invariant. So that's important here that there are some objects which are symplectic and A invariants. And for multi-germs, it's as usual, but sometimes people ask me, well, where is the multi-germs? The multi-germs is as usual, you know, the formulas with adding the number of germs. And now, there is a problem, you see, what I'm talking about here. So we have, it was noticed by Arnold in 1990, I think. Well, maybe later. 2010, I think. 2000. So even if F and G are diffeomorphic and F star, so the pullback of omega of that are diffeomorphic, F and G are not necessarily symplectomorphic. So that's a problem. What is this? I told here that this is geometric kind of restriction, that here was an algebraic restriction. So there are different restrictions. And it appears that the normal intuition is not working for singular curves. And the example is like that A2 case was split it into two cases in symplectic case. So you see there are two cases, A20 and A21, which are clearly A invariant, but also they appeared as a symplectic cases in that. So symplectic codimension of A20 is 3, symplectic codimension of A21 is 4. And this is easy to calculate also the vector space, which is with the unfolding of that, I mean the symplectic unfolding as a basis of that, you see. And then there are differences catched in this way. So the hidden symplectic invariants, which were also Arnold called this as a symplectic ghosts, so kind of hidden things, is like that. If you have a curve, then you see if you have a symplectic structure over, ambient symplectic structure, then that structure, if you restrict omega, then there is also something which is, say Zariski code, or there's some submanifold here, two-dimensional, let's be two-dimensional cusp, maybe three-dimensional, four, but let's two, and which is stayed on that. So then omega on that plane is non-trivial. So if there are differently situated these planes, for example, one is Lagrangian, isotropic, another one not, then they are not equivalent. So this is a very subtle and invisible thing which appears here. And then it's here like that. So you see, if you consider this omega restricted to that, and 1 and 2, they are never symplectomorphic. So these curves are never symplectomorphic, except curves. So you see, this is because these red planes, they prevent for this symplectomorphic equivalency. So that means that they are hidden, they are not visible in some sense, but they are, and the symplectic structure, which is a kind of non-linear, is defined there, you see, in some linear way. In this only linear way, in the point, is the rest is differing the cases. Well, so now the kind of definitions, algebraic and geometric restrictions, let's define this properly. So we have the RAM complex on them and so on. And then we define this lambda kn. There are such forms which are vanishing on n. So that means that omega is vanishing on each tuples of tangent vectors to the space, not to n, because n is not assumed that n is submanifold, you see? It's any set. It's a differential space. Just the set. Whatever, a few points and some things, and that's well defined. And then AK and M is forms which looks like that, where alpha and beta belongs to that vanishing, especially vanishing forms. And then, so that means this is defined here. So algebraic restriction of omega, of the form which is on M, to n is equivalence class. You see, A is, that here is A is algebraic. We will read geometric also. Omega is equivalent to omega tilde if that difference belongs to this form which is kind of kernel form. Yeah. So then this is a kind of zero forms. And then this is subcomplex of the RAM complex. And also this is a homology of this. It's easy to add. We need them for some calculations. So that's just the case for algebraic restriction. Example of algebraic restriction of two forms to AK. So let's have AK singularity. AK singularity, you see, in R2n is defined by these equations. x1 k plus 1, x2 square. But then here all the rest are vanishing. But of course it's possible to move in different way. But this is doesn't matter, in fact. And then let's calculate these algebraic restrictions. Let's calculate algebraic restrictions to n. So first, you see, they look like that, because the rest of x is vanishing. So there is only dx1, dx2. Then, of course, we have, no, this is the function. So this is also zero always, since this is zero. Then we have that, then this is really zero form of an algebraic restriction if f belongs to the Jacobi ideal of function h. So then, all these algebraic restrictions is a finite dimensional space, and it appears if the singularity is isolated. If it's not isolated, that might not be finitely dimensional. So this is finitely dimensional space. And here is this space is k-dimensional. And that's just you see the elements which are spanning this space. And this is very nice idea to show us the way to find all these classifications. Then the Darboux for the singular sets is looking a bit different. You see there is also we assume that the second homology class of that subcomplex is 0, and so on. And then, of course, there are non-trivial cases as well. So maybe. And how to apply this result to symplectic classifications of curves, diffeomorphic to AK. So we can now classify symplectic curves diffeomorphic to all standard classifications, so AK, AD, ADC, IDE. So then the situation is like that. You see, you take this form, which is 0, with algebraic restriction of this form is 0, obviously, if you don't believe, but this is symplectic, it's easy to see. So then the basis for symplectic algebraic restrictions can be represented by this symplectic form plus this spanning element. And all these things are symplectic forms because this one is 0. This is 0 form. I mean, so that's a very tricky method to classify singularities. And then we construct the symplectomorphism, which transform this form, symplectic form, to Darboux form, and then take a curve by the inverse and find the curve, which is really one of the symplectic classification. Well, that's a tricky method. And this way we classify it. Then now geometric restriction. Geometric restriction is a different object. You see, usually we look on F star omega, I mean pullback, as a geometric restriction. We say so. Of course, if F is not, if the image is not smooth, then we extended this definition. We say it's still geometric. But this is defined. These forms, they are geometric restrictions, you see, which are 0 forms, vanishing. So the pullback is 0 for any function, for any smooth mapping F on Z into M from any C infinity manifold Z with Fz included in M. So that's a dynamic definition in some sense. Now then, the class of this element, so you see, omega Gn, that is geometric restriction of omega to n. So of course, if F is, if this image is smooth, then this is simplest case. If not, then it's a bit work. So then we can easily see that these geometric 0 forms have inside algebraic 0 forms. And moreover, this geometric 0 forms is declosed. It's also easy to see. And then then we define the new objects. You know, those geometrically 0 forms, modulo of algebraic 0 forms. So then means that if there are something outside of algebraic 0 forms, which are also geometric 0 forms, that's very interesting forms. That means that there are forms which are algebraically 0, but geometrically not. And then we call them residue forms. This is very, very residuous. And then I show, and of course, this is calculational object. So these are algebraic restrictions with no geometric restrictions. These are such objects, they are just the residues. And there are these exact sequences here, very natural, and also via mapping. If F is image, if some manifold is, say we have a mapping which is, so our singular set is parametrized, so a smooth mapping from smooth manifold Z, then F star omega, this is the geometric restriction of omega by F, which is something like that, naturally. No geometric restrictions by F, we call them like that. So you see, that's the notation also, we can take notation from other definitions. So geometric restrictions by F. This is just the forms by kernel of Pullback, the kernel of Pullback. That's nothing else. Then differential K forms along F, and this is defining just this important algebraic restriction by F. So this is the kernel of that space and the kernel differential of kernel of that space, and there are zero algebraic restrictions for the mapping. And the residues here are defined in this way. For that we have all these cohomologies and so on. If F is an immersion germ, then of course no residues. There are zeros. This is only singularities effect, of course. And then if F is finally determined map germ and the germ of the image of F, then R is vector space, is the R vector space, which is here it is even finitely dimensional. Then example here, you have, say, F which is singular like that, but this singularity is three-dimensional, let's say. Yeah. Then, of course, geometric restriction, zero geometric restriction of that, but not zero algebraic. Algebraic restriction is not zero. So this form restricted to that curve is not zero. That one is zero, you see, because you apply to each x1, x2, x3 this t cube and so on, and then you have zero, but not algebraic. And that's also residuum, which is very natural here to see it very easy. Residues for hypersurfaces. Well, they are defined by Turina number, dimension of that, by Turina number. So this is the situation. Residues for plane curve germs. So residues of symplectic forms for simple and unimodal singularities, symplectic classification of curves. These are just giving the residues. These are residues because if you find the residues, then there are functions which define the curves which are just transformed from the curve which is on which you define the residue. So then, of course, R1 residues are not so easy to define, but that's also is possible. R1, this is for one forms on A2 singularity. So you see this is the Euler vector field. So there are calculations which show this, how does look like these residues. And in fact, this is all what I wanted to say. I mean, this case for us is important because it helped to classify, solve from our point of view, the Zariski problem for classification of diffeomorphic classification of curves, singular of curves, of plane curves. So this is here is a symplectic classification, but as a byproduct we got this classification which is defined by, which is asked for by Zariski. So this is all what I wanted to say.